In this lesson we're going to look at how to curve sketch a polynomial. Now this uses prior knowledge from the differentiation section in Unit 1 and some polynomial work from Unit 2. So to do a curve sketch, what you need to think is where the curve cuts the y-axis and the x-axis, where the turning points are, and also have a wee quick look at the endpoints. It's a good idea to memorise this structure so that when you come to it you can set it out clearly. So first thing we're going to look at is where it cuts the x and the y-intercept. So it cuts the y-axis when x is 0 and cuts the x-axis when y is equal to 0. So when x is equal to 0 we put 0 in here, here and here, and then add on 3. So y is equal to 0 squared plus 0 squared minus 5 times 0 plus 3, and that just comes out as 3. Dead easy, y-intercept 0, 3. The x-intercept in this occasion cuts when y is equal to 0. So we end up having this situation here, and in order to solve this and find the values of x we need to use synthetic division. This is the change from the differentiation curve sketching. So set your table out. What I would do is try 1 and negative 1 mentally. If we can use 1 here, 1 cubed plus 1 squared is 2. Take away 5 plus 3, that comes out to be 0. So let's put 1 into our synthetic division table. If that's a root, then we should get a 0 as a remainder here. So coefficients are 1, 1, negative 5 and 3. Drop the 1 down, then multiply by 1. Add together 2 and multiply by 1 to get 2. Add together to get negative 3. Multiply by 1 to get negative 3, and there you have your remainder 0. Therefore we can get our x minus 1 as a factor, and you can get your other bracket from the bottom here. That's your number, that's your coefficient of your x, and that's your coefficient of your x squared. We can then fully factorise this, because that trinomial will factorise to double brackets. X in the front of both brackets and a 3 and a 1 at the end needs to be a plus 3x and a minus 1x to give you your plus 2. We can then find out where it cuts the x-axis. It cuts the x-axis at x is 1 and negative 3. So 1 and negative 3 to make the brackets equal to 0. Moving on to stationary points. For stationary points you have to use your differentiation and just use your same steps you did in Unit 1. So differentiate this, multiply down with the power, reduce it by 1. 3x squared, multiply down with the power, reduce it by 1. And then it's going to be negative 5. And the 3 will go to 0. Put your statement in. Stationary points occur when the derivative is equal to 0. This is when the gradient's equal to 0, and that's where you get your curves or your points of inflection. So set your derivative equal to 0 here, and then factorise. We're trying to find the x values for the stationary points. So double brackets, 3x and x to give you 3x squared, 1 times 5 to give you 5, and we need a plus 5x and a minus 3x to give you your 2x here. To find the x coordinates here, this bracket needs to equal 0 or this bracket needs to equal 0. So we've got x equals 1, which is easy for this bit. And this, if you want to set it as a new equation, 3x plus 5 equals 0, take the 5 over to be negative 5 and divide by 3. So negative 5 over 3, or x is 1. Now to find the y values here, you substitute these x values into the original equation. 1's easy enough to do, and that works out as 0. 1 plus 1 take away 5 plus 3. Negative 5 over 3 is a bit trickier. I'm not going to go through this right now, but it comes out as 256 over 27. A wee tip is put the negative 5 over 3 in, then multiply the fractions out and try and get common denominators in the bottom. The common denominator you're looking for is 27, and then you can add them and take them away a bit easier. So let's find out if we've got maximums or minimums. So stationary points occur at x is 1 and negative 5 over 3. We need to look either side of these to see what's happening to the graph. A wee bit before negative 5 over 3 would be negative 2, and a wee bit after would be 0. The reason I'm using 0 here is because it's dead easy to use when you substitute it into the derivative. And it's also before 1. We use 0 again here, and then 2 for a wee bit after the 1. So substitute these values in, the negative 2 and the 0, into the derivative. So the derivative's here, so you're subbing negative 2 in here. I'll do that below. So at x equals negative 2, the derivative becomes 3 times negative 2 squared plus 2 times negative 2, take away 5. That comes out as a positive answer, so put plus. The stationary point occurs here, so the gradient must be 0. And at 0, you're just substituting 0 into this point, so 3 times 0 squared plus 2 times 0, take away 5, and that's negative 5, so we've got a negative here. So positive gradient, 0, negative gradient. So that's a maximum turning point at this point here. Next, the gradient at point 1 is going to be 0. We've already worked out at 0 the gradient's negative. We can show that here. And at x equals 2, if we sub 2 in here and here, we get this, and plus 11, so positive. So a minimum turning point there at 1. So just to finish that off, maximum turning point at negative 5 over 3, 256 over 27, and a minimum turning point at 1, 0. So I'm going to highlight these as main points to mark in the graph. Up here, these are main points to highlight in the graph, and that's a main point to highlight in the graph. Okay, y-intercept, the x-intercepts, and your stationary points. We're just going to have a quick look at the endpoints. What happens at very large values of x and very large negative values? Well, as x goes to positive infinity, i.e. a really large number, the cubic function is the most powerful there, so that's going to make everything positive. So as x goes to positive infinity, then y also goes to positive infinity. As x goes to a really small number, a negative value of infinity, when you cube a negative, you get a negative answer. So again, this is the most powerful part here. So when you cube that negative, really large negative value, y will be negative, so that goes to negative infinity. So sketching the graph out, we don't need to do it deadly accurately, but put all your main points in, where it cuts the x-axis, where it cuts the y-axis, and your turning points. And we can see as x goes to infinity, positive infinity, then y, so does y. And as x goes to negative infinity down this way, then y goes away down here to negative infinity. Make sure you mark all your points in your coordinates.